All attendees are in listen-only mode.
Hi everyone, I hope you guys are doing well. And one second, let me fix my audio here. All right, there we go. Excellent. So, if you guys remember from last week, or from Monday, pardon me, we are continuing flight today, but a bit of a change of plans. We are not going to save rockets for next week. We're going to go ahead and start rockets today, actually. And that is because, sorry, we found this really exciting game online that I asked you guys to go ahead and start downloading the tutorial for. If you haven't downloaded the tutorial, that is definitely okay, and there'll be time to do that today. We're actually not going to get to gameplay today at all, but I just wanted to make sure everyone is on the same page for Monday. Right, but before we start with that, I wanted to go over some of the basics of rockets today. Make sure you don't have any questions. Oh, great, Nico. That's excellent. Yeah, it's called the Kerbal Space Program Demo for those of you that missed that note on Edmodo. All right, so since it is around 3:35, we're going to go ahead and jump into lecture. So today we will be talking about kind of how rockets move and what forces go into rocket flight. And it's based on Newton's third law, kind of how the rocket engine works. And in a similar way that hot air balloons operate on this basic scientific principle, rockets work in a very similar way, but with a very different scientific principle. And so that being said, just how hot air balloons started with, or you can make these small models that are really simple, right, that we saw in the Chinese New Year paper bags. We can do the same with rockets, with model rockets. And that's an activity that many people participate in, and it's a great way to kind of explore some of those physics concepts. And when we talk about rockets, since you guys will be building model rockets, we are going to focus on model rockets. They are a way to look at some of the science in a very simple way. And just like there are hot air balloons that are a lot more complex than those paper bag hot air balloons involved in the Chinese New Year, rocket design, I mean, it gets even more complex than hot air balloons by a lot. It is a very, very complicated science. That's where the saying, it's not rocket science, that comes from. But there are a lot of different people that work together to come up with just the design for a rocket before you even get into actual construction. So we're going to keep it more simple and talk, when we're talking about rockets, we're going to be mainly just talking about these single engine model rockets. And that way we can really just focus on the physics and not as much the technical. Any questions before we get started? Jeremy, that's okay. That's definitely okay because we're not going to actually be using the program today. I just want to make sure everyone knows where to get it. Yes, Nico is talking a bit about physics here. Physics, the closer in you zoom in on our universe, the stranger physics gets. Atomic physics is very interesting. All right, so we're going to start with this Newton's third law. And what Newton's third law says is that to every action, there's an equal and opposite reaction. And so I'm going to go ahead and jump out again. Go ahead, raise your hand if you've heard this before. All right, a couple of you guys. Yeah, a few. Oh, Max has as well. This is often quoted in class. No, it's equal and opposite reaction, Andrew. It's equal in the opposite direction, not or. It's and. All right. Yeah, so this is the basis behind how a rocket engine works. And a rocket engine is called a reaction engine. So if you guys think about a steam engine or an engine in your car, those work on propulsion. Kind of that source of energy, like coal or steam, is going to work on making this rotation that builds energy that's supplied to the car or train or vehicle. And that's how a rotation engine works. Rockets are not rotation engines, they're reaction engines. And the way that a reaction engine works is that there's some action, and in this case, it's the burning of the fuel in a rocket that creates this downwards force, the action force. And what happens is that a reaction occurs such that the rocket is forced upwards. The rocket is forced upwards because of this force in the rocket pushing downwards from the fuel. So the fuel is not technically pushing the rocket up. It's the force from the fuel is going downwards, but since it's shooting down, the rocket's reaction is to shoot up. All right. So you can think about this when you have a balloon and you blow it up with air and you don't tie it. You just have the ends kind of between your fingers. And if you let go of that balloon, all the air comes out. What's happening is that the air is shooting out the end and forcing that balloon forward. Okay. So when you look at a rocket launch straight up into the air, you might think that it's similar. You might see similarities to hot air balloon flight because they're both just being lifted up into the air as opposed to how birds or how planes fly using lift. I want to make sure that we see the distinction between rocket flight and hot air balloon flight because they are very, very different. Right? So let's get back into hot air balloon flight. We're going to add a little review here, and I'm going to give you guys the opportunity to answer some questions. So, hot air balloons work by heating up the air inside the balloon, and this makes the air more or less dense. You guys can raise your hands or shoot an answer to that question. Heating up the air. What does that do to the density of the air? Anthony, you're right. Nico, Max, great. Anthony, I'm going to call on you. Anthony, what was your answer?
Less density.
Exactly correct. Just wanted everyone to be able to hear that. It becomes less dense. It becomes less dense. Great, Jeremy. Because the molecules, when you heat up the air, it excites the molecules. They have more energy, so they start taking up more space. Since they're taking up more space, there are less molecules per space, and that means it's less dense. Okay, so we have this now. All of the air inside the balloon is less dense than the air outside of the balloon, and a force is created. And that force that's created opposes the gravitational force, the pull that's trying to keep that hot air balloon on the ground. What is that force that is created because of this less dense air? I'll give you a hint. It starts with a B. Well, it's similar to lift, Nico, but it's called something else. Lift is how an airplane flies. I'll give you another hint. It's also the force that keeps a log floating on water. Nico, exactly correct. And Anthony, that is correct. Right, I'm going to call on you, Nico. What is the name of that force? What's the name of the force?
Buoyancy.
Buoyancy. Great. Yes. So, if you guys remember, when wood is on water, it floats because it's less dense than the water. So what's happening is this less dense object is being pushed down by gravity. But it remains up because of that buoyant force, since it's less dense than the fluid. It is not less dense than the air, however, so it doesn't continue to float up. What's different with hot air balloons is that it would be as if that less dense ball started at the bottom of the cup and continued to float up. Right? A hot air balloon, when it is less dense than when the air is less dense enough, when it's warm enough, or there's enough warm air, that this force, this buoyant force, is strong enough that it lifts the balloon. It overcomes that gravitational pull. So it is called lift here, but I was looking for the buoyant force, Nico. Archimedes, well, the difference between, someone says that air acted like a liquid. The difference isn't that it acts like a liquid, they're saying that it acts like a fluid. So there's a difference between those. And so both gases and liquid, and those are just states of matter, right? Elements can exist in different states of matter, just like water. So they were saying that in the gas and the liquid stage, they act like fluids. Because you can have a stream of air or a stream of water. All right. And so, okay, a couple more questions on hot air ballooning. What are the 2 ways you can control a hot air balloon? Kind of what are the 2 things you can do in a hot air balloon? Yeah, so you can go up or down, and Jeremy has here, warm the air and let the air out. You can open that vent on top, or you can start the burner and get hot air burning into there. And how do you steer a hot air balloon if the only thing you can do is heat up the air or let some warm air out? Max is right. Max says air currents, and that's correct. All right, so I wanted to take that time, review hot air balloons, just so you guys understand the difference between what's going on in a hot air balloon and what's going on in a rocket. They're very different. They're both based on those just fundamental, simple scientific laws. All right, so I'm going to go ahead and jump back into this presentation. So this is these are components for model rockets, kind of what they're made of. We have the nose cone at the tip, and we're going to talk a little bit about why there is a nose cone and what it does. But right now, we're just going to say it goes ahead and it reduces aerodynamic drag. We'll talk a little bit more about that. The body tube. The body tube holds all the internal parts of the rocket, like the parachute. And it connects the nose and the fins. The launch lug is this small tube that it goes on the exterior of the body tube, and it's the part that holds the rocket to the launch rod when the engine is pushing the rocket up to a safe liftoff speed. So you're going to have a launch pad and this thin wire that comes up from the launch pad. And you attach your rocket, you kind of slide this launch lug over that thin wire so that as your rocket begins to rise, it rises straight and doesn't immediately fall to the side. And this is for safety. You don't want right as the rocket starts to take off for it to take off close to your head or your eyes. And then we have fins, and we use fins to stabilize, or they provide stability. They're like a stabilizing force to keep the rocket moving along a safe trajectory. All right, and here's the flight profile of a model rocket, kind of the stages it goes through. Ignition and liftoff. And so you ignite the rocket. It immediately starts, or not immediately, but once it reaches about 35 miles per hour, it is officially lifted off. It has enough thrust and goes into the air. All of the propellant inside of it gets burned up, and once it's all gone, you hit the engine burnout stage. But what happens is there's a stage of coasting where it continues to move forward, or move upward, that is, even though the propellant is no longer being burned. Up at this top level, that nose cone is ejected. And we'll see there's like a little spark left in your engine, and that pops that off, and your parachute will pop out. And that's the ejection and then the recovery. And here we are comparing kind of the model to the real thing. We're going to spend too long on this because we're going to have plenty of time to look at what a real rocket looks like when we play the game and we design our own rockets. But here's the nose cone, the body tube, the motor. You can see the motor is a lot larger when you have this huge rocket. And then that's a nozzle for ejecting kind of the fuel. And this is where our fins. A rocket's not going to have fins. It's going to have more advanced stabilizing methods than fins. Here are kind of how the fins work and how they should. There are different names for the different edges, and since you guys are going to be building, this is more important for the day that you will actually be building, but it's important to understand that the fins, the different edges, have different purposes. And you can't just stick it on any which way. This is the way you would stick it on for most stability. All right. And here are the different types of model rocket recovery. We talked about the parachute recovery, and this is a way, especially if you worked on that rocket for a long time, this is nice because it slows down the rocket's descent, and so it won't crash as easily. The streamer recovery method is one that I used in school. It's nice because you're able to, it slows it down a bit, but more what it does is you can see that streamer easier from a further away distance, so you can go find your rocket. Got the nose blow recovery, which just separates the nose. Again, it's going to slow it down a little bit. Tumble recovery. This is pretty much if you don't have a recovery system. And then glide recovery, it would just have those wings, so once it reaches that peak moment, it could kind of glide a bit. Same with that helicopter. We're not really going to focus on these. If you think about, weight is really important, and so is being aerodynamic, and these might add more weight than you would like. And so we talked a little bit about already how these engines are reaction engines, but here's just another way of looking at it with the force. The force of the gas, the force of that propellant is going to push that way. And this is going to cause a reaction that forces the rocket this way. similar to how a cannon would shoot a cannonball. Do we have any questions? No questions? All right, great. Here is a cutaway of a black powder engine, similar to the ones that you'll be using for your rocket. We have this, it starts from down here, the clay nozzle, and this is where you kind of put your wires in to ignite. Here's the kind of the fuel, the black powder propellant that burns through, and it gets to this delay composition for the part of the rocket flight where you're just gliding. Because after you get through this delay composition, you get to the ejection charge, which is going to burn and pop off the nose and maybe the parachute of your rocket. You don't want that nose and parachute to get popped off as soon as you run out of the black powder propellant, because that's going to mess up your the gliding section of the rocket when it's still moving up, even though you've run out of propellant. And you guys can think about this, like, you know how your body keeps moving even after you've slammed on the brakes in your car, or if you're jumping on a trampoline and you jump, you're going to still continue to move upwards even after your feet have left the trampoline. It's the same with the engine. The same with the rocket. The engine is going to force it up a certain amount, and it's going to keep going until gravity starts pulling it down. The rest is going to keep it alive until it starts to go down. So the delay composition is there, and it slowly burns through the delay composition, and then the parachute will shoot out. All right, and we actually have a step-by-step again, so you guys can see how this works. A little more clearly. All right, so the first step, the igniter is inserted into the engine and held in with that plug that you saw. So that way that when the electricity is going to flow in through those clips that were down here, and the plug is going to keep it all together. When electricity flows through the igniter, the wire heats up and causes the pyrogen at the tip here to burst into flame. This ignites the propellant in the motor. The black powder propellant quickly burns and creates the thrust that pushes the rocket into the air. In a black powder propellant engine, the flame front burns from the rear toward the front edge. After all the propellant is consumed, the delay composition starts burning. It burns slowly and does not produce any thrust force. During this period, the rocket coasts upward and gradually slows down. The smoke produced by the burning delay composition helps you see the rocket in the sky. The ejection charge ignites immediately after the burning delay composition is consumed. The fast-burning ejection charge overpressurizes the case and bursts through the clay cap. This also pushes off the nose cone and ejects the parachute out of the body of the rocket. At this point, the rocket descends slowly to the ground. The engine cannot be reused. So I guess what they're saying here is you can't really refill this with propellant, right? Because there's not going to be any propellant on it at this point. You're going to have to go ahead and get a new engine. Yeah, it is, Nico, it is like stages of a NASA launch. In a NASA launch, you do see kind of the rocket come apart too, which is cool. All right, any questions? Great. All right. So when you see that C 6, 3, they have all of those, like the letter and the two numbers, they have different meanings. The very ending number tells you how long it's going to take to burn through this delay composition, so how long the delay is going to be. And you can tell which kind of engine you want to use based on how windy it is. You guys will get more into some of this stuff when in high school. Here we see thrust, and thrust is that forces the rocket up. We see this thrust curve, and what happens is that thrust is the most right when you launch the rocket, and then it kind of levels out as the flight continues until there's no more propellant, and then there's the burnout. So right when it catches flame, you have the most thrust, levels out as it starts burning steadily through the propellant, and then decreases as soon as it runs out. And this is just a little diagram. The different motors produce different amounts of thrust. We're using a C motor. And this is letting you know what kind of field you're going to use with the different motors. And by what kind, I mean how big it has to be. And this is important. As you see, the trees are kind of in the perimeter. You don't want to be working in an area where you are too close to trees or roofs, because it's going to make it really difficult for you to go get your rocket if it's stuck up on the roof or stuck in a tree. You want to make sure you're in this open field far away from those from anything that your rocket could get stuck in. Obstructions, there we go. And knowing the type of the rocket, you'll also know about how high, the approximate altitude it will reach. And of course, this is based off of you having a high performance minimum diameter rocket. So you have to put it together correctly, make sure everything is smooth and nice for it to reach these altitudes. If you did a bad job, you don't sand it well enough, it's too heavy, you use too much glue, it's not going to reach those altitudes. In this diagram, we kind of see the different forces working on the rocket. We talked before, gravity, and that's going to be from the center of mass. Here, the center of mass is probably going to be a little bit more towards the bottom, but that's going to change as the propellant is burnt up. Propellant is very heavy, and in a real rocket, fuel is incredibly heavy. So the longer you are in flight, the weight of the rocket and the weight distribution is going to change. So your center of mass will actually change. But the gravity force pulls straight down towards the center of the Earth from that center of mass. Your thrust force is coming up from the engine, and there's another force coming down called the drag force. And drag, it's similar, think about having your hand open underwater and spread out and trying to pull your hand through the water versus having your hand as a fist. It's going to be easier to pull the fist through the water because there is less drag. It's all about the shape and how easy it is able to move through the fluid. So the smoother, more aerodynamic shape that you have, the less drag will be created. And this is important on the airfoils as well. These are kind of cross sections of those, as if you were looking at them as a cross section, like straight on. You can get, it might come square, but what you're going to want to do is either round the tips, or if you can, streamline it, but it has to be symmetric for this to work and still be stable. And this will reduce drag as well. And so this is called Form drag, it's the most significant. It's related to the shape. Skin friction drag, you got to make sure things are smooth. You want to reduce that surface area, and you can do that through sanding. And interference drag, it's just the way that the air is going to move over the rocket. We don't have to worry about that as much. And same with induced drag. All right, so before we get into our game, let's see if we have any questions. Okay, Robert is asking, can we know a little bit more about the different kinds of motors and what they do based on wind conditions? Sure. So the different kinds of motors are going to take your rocket. They have a different amount of power. And so the larger the size, the more altitude that you are going to be able to reach. If you have a really strong wind, you want to use a lower number delay, because the wind is going to, you want to shoot out your parachute more quickly, so that way you're not shooting out your parachute once you're already almost at the ground. Wind is going to interfere in that way. So if you have a strong wind, you're going to want to use a shorter delay so that your parachute can get out in time. Oh, Nico, the delay is in seconds. I see that you asked that before. I apologize. All right, any other questions? All right, so before we get into the game, I wanted to show you guys a short clip that goes into kind of the different jobs associated with designing and engineering rockets. So we're just going to watch a little bit of this. Start from there.
Engine system, a main propulsion system, a communication system.
So
There's parachutes, there's avionics, there's electric cabling, miles and miles and miles of it. So many different parts and so many different pieces.
Well over 1 million parts on the line.
So they're talking about a rocket that would take you into space right now. We're just talking about what the design is there.
Vehicle.
You know, in a house you've got plumbing.
Hold on, someone had a question about delay. Robert, I'm not sure what the delay material is made of. I'm sorry. It's just going to be a slow burning material that is not highly combustible because it will not produce thrust.
In a house you've got wiring, you've got structures. Well, our house has to fly.
Engineers are all about solving problems. That's really our job title, is solving problems and making something useful. My job is a system engineer, and that basically means that I'm responsible, and the people that work with me are responsible for making sure that this extremely complex launch vehicle all works together.
I'm an integration project engineer.
So I want you guys to be especially just listening to how different these people's jobs are, how much responsibility they have, and how much of rocket design is these different teams working together.
Part of being an integrator is to make sure that the system works as a whole. You have a lot of individual components that when they work by themselves, that's great, but they need to work all together for a successful vehicle.
One of the things we do in engineering is to create models. This is one of our performance analysis design demonstrators. Fancy word for an engineering model. Here's one of the locations, potential locations for that electrical interface.
Okay.
And let me come around here and show you a couple of things that we're thinking about for the.
I work on the upper stage of the Ares 1 project. My job is to be sure that all the little pieces to build the rocket fit together.
You can do models with different types of construction techniques. We've chosen for this model to use plywood and 2x4s and PVC pipe and foam board and things like that. This is a mock-up of our inner stage, the piece of structure that connects the first stage of the Ares launch vehicle with the upper stage of the Ares launch vehicle. When Ares is on the launch pad, there will be ground crew that will have to come into this space.
People down at Kennedy Space Center, they're going to have to work on it. They're going to have to be able to go inside the vehicle. Did we leave enough room for somebody in there connecting cables?
The J2X engine is represented by that center section of our mock-up. The exterior volume of that engine bell is represented by our PVC pipes. It gives us the ability to take a look at the size and shape and volume of this J2X engine in relationship to all the other pieces of equipment in the interstage. The engine is an extremely complex piece of machinery, and it requires a lot of equipment to make sure that it can run and to operate safely.
It's such a huge task. But if you break it down into the parts and just deal with them one thing at a time, then it's doable.
That's right behind us on the door here, and we moved it from inside 90 degrees.
That's great.
We're sitting in our collaborative engineering and design analysis room. Technology has come a long way between the time we designed Space Shuttle and what we're doing now with the Ares vehicle.
And even further since this video was made.
All of our designers now are designing their parts in the virtual world. They are actually designing three-dimensional virtual parts.
Here at Marshall Space Flight Center, we take those parts and put as many as we can together to build a virtual mock-up of the vehicle. We take it and begin to analyze it. We can go in and actually fly through the vehicle. Basically, from a click of the mouse, I can go anywhere on the vehicle.
Roosevelt, can you fly us up into that frustrum region? And let's go take a look at that joint. We have the ability to do three-dimensional projection. We have special glasses that we put on so we can really get a sense of the size and shape and volume.
All right, we're not going to go more into this, but what is also cool is that they can take those 3D models and run them through trials based off of physics that they're going to encounter in the atmosphere, and make sure that everything is going to work before they build a model of, kind of one of those PVC pipe models that you saw in the beginning. What I thought was really interesting to keep in mind are all of those considerations they had to make just about the crew that was working on it, without even considering the challenge of going to space. They had to keep in mind, well, real people are going to be here. They have to be safe. They have to be able to get to all these parts. Really interesting. And these are things that you guys are going to have to keep in mind as we start to work on building our own rockets using this Kerbal Space Program. The Kerbal Space Program, KSP, is a game where the players create and manage their own space program. You build spacecraft, fly them, and try to help the Kerbals, which are these little alien guys, to fulfill their ultimate mission of conquering space. All right, so I asked you guys, and I'm going to send this out over chat as well. I just want everybody to be able to have this software for Monday, so it's okay if you cannot download it today. But I will send out another reminder this weekend. Go ahead and send that out through chat. All right, and we are doing the demo for now. There is a full game I believe it costs $25. But for now, we are just going to use this demo just to do some of the basics and exploring what goes into the engineering of a spacecraft. What do you have to consider in order to get the rocket off the ground, in order to keep the rocket stable in flight, and in order to bring the rocket home? Because we're going to bring our Kerbals home. We don't want them just floating around space. Yes, Nico says $23.99. That's exactly how much it costs. Okay, Will, you're not gonna, you need to download the demo, not, yeah, you've got to download the demo. It's down here, either for Windows, Mac, or Linux. Nico says he was looking through the game and he looked at a part and the manufacturer was found on the side of the road. And that's what's really, I think, fun and interesting about this game, is that you are kind of given this role of, you have all the parts available, and we're going to learn together on Monday and Wednesday how they go together and what you need for space flight. But you have to make all these considerations depending on the price, the cost of the tools, and how well they were constructed, how much power versus stability that they have. And then some of the parts, they're not even integral or useful at all to a rocket. They might just have a name that you think, oh, maybe I need this. So that's funny, Nico. Oh, great. Well, all right. So I sent it out to everyone. And when you go to that website, this is what it will look like. The little Kerbals. And order now. This is if you wanted to order the game. But we are going to get the demo version. And it takes a little while to download on your computer. That's normal. Someone in my last class brought this up, that they were worried it wasn't safe. Mr. D and I thoroughly check out things that we ask you to download. We try not to ask you to download too many things. A lot of times we'll play those games in simulators, and I'd rather just use Java or Shockwave Player because downloading can be risky with a computer, but we know for a fact that this demo is going to be safe for you guys. All right. And so I'm going to run through a little bit of my presentation about the basics, and then I'm going to show you guys the game that I have on my computer so you guys get a little excited about what's coming up on Monday. So this is what's going to pop up. You're going to click Start Game and Start New. You can also go into Settings, and I can show you guys how to turn off that music if you don't want to be stuck listening to that music. And it opens up to this big screen, and you this is called your Kerbal Space Center, and you see the different buildings and what they do. All right, so the tracking station, you can check on the progress of your missions, and that's this satellite here. You have the VAB, where we're going to be spending a lot of our time, and that's the Vehicle Assembly Building, where you build rockets. That's here. The launch pad, where you launch your rockets. That's here. And the space plane hangar, where you build planes. And that's here. All right. So we are going to be using a tutorial created by Senshi. It was a wiki that was created for the game. And I just wanted to give a shout out as a thank you for making that available for everyone, where we go into basic rocket design and kind of the goal of that that we're going to be accomplishing. Not massively surprising, but we want to overcome gravity and drag. And to do that, we're going to make our rockets light, smooth, and give them plenty of power. So for our first rocket, we just want it to be simple, but also able to overcome that gravity and drag. And these are our biggest obstacles. And so on Monday, we're going to talk more about this, but instead of just figuring out what the parts do and trial and error, putting them together. We're going to construct our payload first. We're going to talk about more about what that means on Monday. And then we're going to construct a launch vehicle modeled on that payload. All right, so we're going to construct exactly how much it needs to weigh, just bare minimum, and then how much fuel and thrust we need to get that up off the ground. All right, and now we're going to go through and learn a little bit about some of the placement helpers that Kerbal Space Program has in their game, and just kind of the basics of how it's set up. Wow, Nico said he went to the vehicle assembly building at NASA last year. That is very cool. All right, so I'm going to go ahead and open the game so that you guys can experience it, those of you who haven't downloaded the demo yet. All right, so we're going to go ahead, press Start Game. You see I don't have the music, and that's because I went to Settings, Audio, and I have I turned down all of my audio, but I can still hear the voices in the spacecraft a little bit. In terms of, okay, I might try to change my graphics here. I'm doing that because I'm having trouble seeing everything on my screen. It's making my screen a little bit too big. So let me put that again. You go into Start Game. And then you can go ahead and start new. And here is the center. You have your spaceplane hangar, your vehicle assembly building, your launch pad, and your tracking station. And we're going to that vehicle assembly building. And here you can see the different options that you have that we're going to go through. As we start to build our spacecraft, we can name it something so that we can save it and load it later when we want to continue working on it. And then here, this is make a new spacecraft. You could also press this button to try and launch the spacecraft you're working on, or this exit button to get back to this area. All right, so this is our command pod. It's a module. And if you look, it says that minimum crew to operate, that it needs at least one little guy to operate it. All right, so if you have the full version of the game, you can actually have unmanned flight. So none of our Kerbals would have to go to space, but we have to send at least one Kerbal to space, which is not ideal if we are new to rocket design, right? We don't want to risk our Kerbals' lives, but we'll be sure and build a really safe rocket before launching it. But once you have that module selected, you can go into building these other parts, and they're broken. This is our pod. They're broken into propulsion, control, structural, aerodynamic, utility, and science. And we are not going to have as many options as the full game, which you see through the tutorial, but we will have enough to build a rocket that can go into space. And you can kind of see when I would take maybe this fuel tank that they fit together vertically. And that some fit on the side. Here, let me add this fuel tank to the bottom. Like this landing strut fits on the side. And what you can actually do is hit this symmetry mode down here. And as you increase it, now when I put up just this one leg, a symmetrical leg is set on the other side, or a leg is set on the other side, symmetric to that leg. I can hit symmetry mode again, and now 3 legs. I can hit it again, and there'll be 4, etc., all the way up until 8. And then it's just back to that 1. So you can kind of click and toggle through the different symmetry modes. There's also the option of angle snap, and that breaks where you can place these different things into 22.5 degree markers. You can't place it anywhere now on the rocket. You can place it kind of 22.5 degrees apart from each other. And this is good, and this way everything's going to align a little bit smoother. And same with the symmetry. It's important to have good symmetry and good alignment on your rocket and not just kind of random placement. And this will create a really solid center of mass. Steven asks, what happens if a Kerbal dies? I'm pretty sure it's like another video game where just, another Kerbal is there. I don't know if they go into as much detail about what happens when your flight crashes with a Kerbal inside, but my crew is very nice. I don't want to risk their lives. All right. Gonna finish out kind of explaining the buttons on this here. We have these here, which just let us know where our center of mass, center of lift, and center of thrust are. We've already talked about center of mass. That's going to be in the middle of our weight distribution. So if the top is a lot heavier than the bottom, then our center of mass is going to be closer to the top. Center of lift isn't something we're really going to have to worry about. That's more to do with planes. But center of thrust is centered around wherever our fuel source is going to be. All right. And so that kind of goes through. You can press reset. I thought that would reset it. I guess I am wrong. You can go ahead and save your spacecraft and then load it later. And we are not going to go more into building a spacecraft today. But now that you guys have a basic idea of how these buttons work, do explore the different options. I want to make sure everyone's on the same page that on Monday and Wednesday, we're going to go through and start from the very basics. So if you start this weekend and just like tear through the game, that's great. I'm glad you're excited, but do understand that come class on Monday, we're going to be starting at the very beginning. Make sure everyone's on the same page. We're also going to be going about it in a very engineering method way. But I will say that we're going to have really solid rockets, as opposed to rockets that are kind of thrown together haphazard, like this one is starting right now. All right, does anyone have any questions? Does anyone have any questions on how to get this Kerbal space program? Again, it is available on this website. I posted it already on Edmodo, and we do want that for Monday. All right, so we have about 4 minutes left in class today. And are we sure no one has another question? I'm just going to go ahead and continue this movie from before. And that's really going to be it, but I'll be here. If you have a question, go ahead, raise your hand or send it to me, and then continue the movie.
Associated with all these various parts. We can actually go inside the fuel tank, take a look at how things are put in there, go take a look at our instrument unit, where all of our flight computers and navigation equipment is.
Someone has a great question. Will, I had a similar problem. Will is saying that he changed the audio settings but can't figure out to get back to the game. What might be happening to you, Will, is that since you are in the window mode of the game, you can't see the bottom of the screen. You have to hit apply and then hit accept. If you go into full screen mode, which should be an option for you, up somewhere at the top, kind of maximize your window, you should be able to see those options.
See if there's a better location for things.
We can see where interferences are.
Seeing that everything's going to match up the way it's supposed to. The last thing we want to happen is for all these pieces to get shipped and get down there to stack the Ares 1 and find out something doesn't fit together. We have to find those things out long before the vehicle ever ends up at Kennedy Space Center.
Building a launch vehicle or any other integrated system requires teamwork.
We have design teams literally spread across the country.
There are thousands and thousands of people that work on and support the Ares vehicle.
You have to have all those people involved in all those groups and all those teams because we're all important. We're all part of that same big team with one goal in mind, and that's for manned space flight.
There's tremendous opportunities. You do not have to be an expert in everything to work in the space industry. The folks that I like to try to recruit just out of college to work with me are the ones that are extremely innovative, extremely creative, but have a very good foundation in traditional science and the traditional math.
Something that you have to be able to do is be courageous enough to ask the question. Not everybody knows all the answers, and it's really hard when you're brand new on a project and you're the only girl in the room and everybody else has 20, 30 years on you. Being able to say, I don't understand, or this doesn't make sense. And the worst thing that can happen is you're wrong and somebody will explain it to you and you've learned something new, or you're right and we're missing something and, we've now solved a problem because you offer a different perspective.
For the student that's in 10th grade, I would tell them there are many avenues in the space industry that are just limitless.
All right, guys. I hope that you guys are as pumped about the Kerbal Space Program as I am. And I think you guys are really going to learn a lot about the physics behind rockets by being able to put them together. I will see you on Monday. And again, if you guys just have that downloaded for Monday, I'd really appreciate it. Bye, guys.